Okay, thank you, Martin, and thank you to everybody at the International Association of Relativistic Dynamics. I'm going to go over to my slideshow now. My name is James O'Brien. I'm here from Springfield College, and I'm giving this talk for the International Association of Relativistic Dynamics entitled Alternative Gravity in the Bottema 2015 and Carrignan 2013 Samples. A couple of acknowledgements first before I get started. Thomas Chiarelli, graduate student of mine, not at Springfield College, but a person who worked with me in this work for a long time. Philip Mannheim, my old PhD advisor, who we still work very closely and collaboratively on all materials related to gravity. William Karen, one of my undergraduate students at Springfield College, who is beginning some work with me now. He's an aspiring freshman, and so he's getting involved in this work very early, which is very exciting. Space Chekhov, a former graduate student of mine who is currently at UMass Lowell. And he's always been helpful in discussions and getting some of this work going. And Physics Letters B, which is where some of the work that I'll be showing today was published. So again, I want to say thank you to everybody who is up at very early times at different locations around the world to hear this presentation. And I look forward to taking questions at the end of this presentation. So I want to give a brief overview as to what this talk will entail. We're going to be talking about two different galactic surveys. And in those galactic surveys, namely the Bottema and Carrignan surveys, I'll be talking about rotation curves for some alternative gravity models, such as MOND, Modified Newtonian Dynamics, Conformal Gravity, and the McGough-Lele-Schoenberg formalism, which will be explained a little bit later in the talk. After that, we'll talk about a Tully Fisher analysis for both MOND and conformal gravity in these two surveys, and how the Radial Acceleration Rule applies for MOND, conformal gravity, and the McGough-Lele-Schoenberg formalism. So let's first talk about what a rotation curve is and why it's important to this work. Okay, this work goes back to the famous scientist Vera Rubin, okay, who first had the idea in the early 80s of pointing a telescope, an optical telescope in particular, at galaxies. So not at individual stars, but pointing at the galaxies. And what she would do is she would point them first at the center of the galaxy, which is located at point B here, and span the telescope out towards the edges of the galaxy. As she went one way, the galaxy is obviously spinning, and so some of the light at point C is moving away from us, some of the light at point A is moving towards us, and so at point A, some of the light that's coming towards you is blue shifted. At point C, the light is red shifted. If it's blue shifted and red shifted, it means that we can use the Doppler effect to calculate the actual velocity, the rotational velocity of these galaxies as a function of the distance r from the center of the galaxy. If you do that, you get a very famous looking picture. This is one for M33 overlaid on an optical image of the galaxy M33. And we can form what we call in the field a rotation curve. And a rotation curve is a plot of that velocity as a function of distance, okay? And if we look, then what we typically get is we get points like these yellow dots. These are the actual data points from the optical disc. And then as you look past the actual optical disc, we can still get more data points. This is from radio waves in the radio telescope regime. And we get data points that look like those blue dots with the error bars. And the interesting thing about this is that it's not unique to M33, but basically for every galaxy that we've observed in the night sky, if we look at the way that those data points are trending versus what the Einstein expectation is, which is that dashed line, we are in total disagreement, okay? And so here's some real examples taken from a sample back in 1986. This is some galaxies that I used for my PhD thesis taken by Begeman. On the left is NGC 3198, a very large spiral galaxy like our own, and DDO 154, a very small dwarf galaxy, way different scales on the axes, as you can see. And what we see in these two samples is that no matter what the size and shape of the galaxy, this discrepancy of the data, the blue points with the error bars versus the actual predicted line is always, they're just not in agreement. And this is a real problem for physics because, you know, in physics, we need to have the agreement or the prediction matching the actual data. And this is just not the case, okay? I have a small video here that can illustrate this. On the left is what we actually see in the night sky for a particular galaxy. and on the right is what we predict the galaxy should actually be rotating. And as we can see on the left, these stars are moving way faster than we expect them to be based on the current theory of gravity and general relativity on the right. And when we have one of these discrepancies, it means that we have to have some way of explaining this. Okay, so how do we first get that prediction? This is all a review for everybody in the room here, I guess in the virtual room. But how do we get this, this prediction? Well, Einstein told us what the gravitational potential for a single point mass, something like a star or the Earth, would be due to the curvature of space and time. It's given by this equation beta star up here. And we extrapolate from that one mass out to a galaxy using superposition. What is a galaxy? It's basically a one-dimensional slice of a three-dimensional cylindrical coordinate system. So we can integrate that gravitational potential over the entire disk of the galaxy. And we do that for an exponential distribution, which pretty accurately describes a spiral galaxy. And what we get is as an output is we then take that net potential and we compare that to the kinetic energy that that galaxy should have, 1/2 mv squared. And from that, we get a prediction for the velocity as a function of the distance, which goes like the mass. And it goes like this formula down here at the bottom. And this is the famous Freeman formula, which gives us that prediction that we had back in these lines, this blue line here, okay? So if we have this discrepancy, though, where the data is not matching the actual prediction, then the current mainstream solution to this is that perhaps there is some dark matter on the outside of the optical disk, which is confining this luminous matter in such a way that the dark matter interacts with the luminous matter, is pulling it to speed up in some ways, and thus it's giving some other contribution which we can't see, hence the words dark matter, okay? And so if we take something like the Milky Way galaxy and ask ourselves, well, where would the dark matter be? It would be, again, outside of the main optical disk, okay, which causes the rotation to change. The dark matter formalism, we'll use the typical NFW type formalism, which has an overall density of the dark matter, the sigma function here, at some critical radius, maybe how far out the dark matter is distributed. That's the little parameter R0 there. And so we can use the NFW formalism to suggest how the dark matter is going to contribute to those rotation curves. And again, I have another video to illustrate how this goes. If we look then for this galaxy, the Milky Way galaxy, this is one of the modelers that Robert Moss, one of my previous students, developed, okay, is that we see here on the graph, the green is the Einstein-Newtonian general relativity prediction. The black is the net contribution from the dark matter, which is in orange, with the green. And if we adjust the dark matter density and the dark matter halo radius, we can eventually get the black line to be in pretty good agreement with the data, okay? Now, this has some problems though, right? Because since we can't see, touch, taste, or smell the dark matter, we don't have beforehand a knowledge as to how dense this dark matter density should be, nor do we have an actual value for that parameter R0, which is why you see in the video here, me adjusting those parameters to get this to fit. That is very problematic if we're talking about making actual physics predictions, especially if we have to do this across an entire spectrum or morphologies of galaxies, from ellipticals to normal spirals, barred spirals, and all the rest. Okay, if we don't know those two parameters beforehand, then what we're really doing in a lot of ways is curve fitting. And if we have two free parameters, well, technically three, because we also don't know the net mass of the galaxy, we have good estimates for it. I'll touch on that later. If we have three free parameters per galaxy, then of course, no matter what that function is going to be with modern technology and computing power, we can definitely get a good functional fit for this. And when we do it, if we're going back to these animations from before, then we see here that now we can make the rotations on the left match the speed of the rotations here on the right by inputting a certain amount of dark matter at some critical radius, okay? That's the overall dark matter formalism and how it works for sets of spirals. I want to touch now on a very modern piece of physics that has only come out in the last 3 years, okay? And this is something that has been recently named the Radial Acceleration Rule, okay? This came out from a paper by McGough, Lele, and Schoenbert, okay? And what they found was a very interesting relation. is that when I showed you those two galaxies earlier, the large spiral and the small dwarf, if I was to take those two sets of data points and put them on one axis, it would look like a scatter plot because the axes are so far off, the galaxies look so different. It looks like there's almost no correlation between the physics that goes on in a large spiral and a small dwarf. Okay. However, what Magoffalele and Schoenberg realized is that you can do something very interesting. Simple physics tells us that instead of measuring the rotational velocity as a function of distance, what if you instead measured the centripetal acceleration for each one of those data points? Namely, just take that velocity at that point, square it, and divide it by the r position. Okay, and so they did that for both the observed, this is the g ops, v squared over r, and the g bar, that which is predicted, the v squared bar stands for the baryons for the luminous matter, so v squared over r, and then make a scatter plot of your v squared ops over r versus your v squared r baryons. And what we see is that when they did this for 153 galaxies using the total of 2,693 data points, okay, you get a curve which looks like this panel here, which is not a scatter plot. This is a nice tight plot which looks like there is some correlation between the baryonic luminous matter alone and the observations. Okay, clearly if you look, it's a little bit hard to see in this picture, but there is this dashed line that goes down in a constant slope of 1. This is the line of unity. If the points all lied on the line of unity, then we'd say there would be no need for dark matter. Right? Here's a better illustration of that here. But since there is a departure from that line of unity, maybe this gives us a mechanism for constraining the amount of dark matter in these galaxies. But this not only constrains it, this would provide some insight into a universal way of piping dark matter into it. However, in their paper, they had 3 possible conclusions that could be drawn from this figure. And the one that we're going to focus on here is conclusion number 1, that this figure represents, is conclusion number 3, which says that maybe this figure is producible because it is the result of new dynamical laws rather than dark matter itself. Namely, is there some other dynamical law which might put, instead of this correlation, might put the data points all along the line of unity? And that's one of the things that we're going to be discussing. So again, just to explore how this actually comes to fruition, I want to give you some examples here. Here's 3 spiral galaxies, okay? The data points in black, the prediction in blue. And if we take those data points and for each one of the velocities and the radius, we take the velocity squared divided by the radius, then we can occupy that sector of the centripetal acceleration plot below. We do that for each galaxy and add them up, and we will slowly build the radial acceleration rule plot galaxy by galaxy, point by point, that was shown in the previous slide. So this galaxy has 48 points, this one has 67 points, the next one has 80 points, right, yada, yada, yada. And so we're adding these all up as we go. And if we just let this movie play through, and this movie can be found at Magoffalele and Schoenberg's website about the radial acceleration rule, we can see how we're building this plot. You can see the points are remaining in a lighter blue there. Depending on the size and shape of the galaxy, this is how the plot is generated. I'm going to fast forward that all the way to the end, just for simplicity's sake. And we get to that plot that we have there. Okay, now, the main alternative theory of gravity that I work on is conformal gravity, and we're going to see if conformal gravity and also modified Newtonian dynamics can explain some of these things that we're seeing. So in order for us to start with conformal gravity, I don't want to go too much into detail because many of you have heard me speak about conformal gravity in the past. You've heard Philip Mannheim talk about conformal gravity in the past couple of years as well, okay? But the nuts and bolts basics is, instead of starting from the Einstein-Hilbert action, okay, we are taking a covariant or a metric theory of gravity. So gravity is still the curvature of space and time, okay? But instead of starting from the Einstein-Hilbert action, we're starting from the conformal Weyl action, varying it with respect to the metric tensor in order to get an equations of motion, which are different from the Einstein equations. And so if we have a different Einstein equation, we can expect a different solution. This can actually be solved for a Schwarzschild-like metric, namely for a single point mass. Okay, it is somewhat of a beast to solve, but this was originally solved by Mannheim and Cazanis. And what we see is that at the very bottom, the solution looks much like Einstein. It contains the first two Einstein terms, but then it does contain a deviation term, which grows linearly with distance. But we can't stop there because conformal gravity is not just a local theory of gravity, it's also a global theory of gravity, so we can't assume things like Gauss's law. And so if we then see what the cosmology has to offer in this, we go through all the mathematics, what we see is that that linear term, which started by just being a local piece, now gets extended to being two linear terms, one that is coupled to the luminous matter, but then a linear term which is not coupled to luminous matter, so it's a universal term, as well as a quadratic term, and the constants of integration are given below. References will be provided at the end to show how this goes. Now, what this buys us is that if we're talking about rotation curves, it means that conformal gravity is the only alternative theory of gravity right now that does eventually predict the rotation curves to eventually terminate. Instead of just hanging up and being constantly flat, like the NFW dark matter would do, or something like MOND, the rotation curves would eventually fall over, and in the largest of spiral galaxies is where you could possibly observe and have this be testable or falsifiable. And we do have a set of galaxies. We published a survey a couple of years back in PRL about how the 21 of the largest galaxies that we ever observed have started to show this fall off. Okay, but the samples that we're going to be working on today for both for the rotation curves, for this radial acceleration rule, and also for Tully Fisher, which we haven't introduced yet, are these two surveys that we discussed in the beginning. Okay, why did we pick these two surveys? Well, 2015 is fairly recent, 2013 not so much, but we picked these surveys for a few reasons. Number one, they're quote unquote high resolution galaxies. They're very, very well studied. Number two, they span a diverse mix of dwarf and large spiral galaxies, so it spans the entire spectrum of galaxies. They all have well-known distances. And so those of us that are in the game of doing large-scale physics, we know that any one of these measurements are super sensitive to the distance that you use. Some of these have bulges and some don't, but more importantly, that these two papers or these two surveys, when they were originally written in 2015 and 2013, they were said to be problematic for the alternative theory of MOND. As the literature goes, if a sample of galaxies is problematic for one alternative theory, then it must be problematic for all the rest. Hence why we're interested in this survey in particular. This is the actual data for the 2015 Bottema survey. Okay, I draw your attention to the left foremost columns, which are the input columns, and we see based on the luminosity and distances here that these are greatly varying in terms of size. Okay, the rest of the columns are going to be our output columns, and we'll come back to those in a minute. Okay, so in each one of the plots that we're going to show, we're going to have a couple of different curves on here. The blue curve is going to be that which is predicted by conformal gravity. The red curve will be predicted by MOND. The green curve will be predicted by if we reverse engineer the Magoff, Lele, and Schoenberg centripetal accelerations to give us a value for velocity, what their curve would be. And then the dashed one would be the Newtonian prediction without dark matter, which is obviously in most cases going to miss. Okay, and we see for the Carrignan, I'm sorry, for the Bottema sample, if we let conformal gravity be the theory which sets the scale or sets the mass, if we look at the column on the right, we see the mass to light ratios are acceptable mass to light ratios. They're hovering right around the number 1, which is what we would expect if there is no dark matter. And we see in all these cases, the blue line gives a way better prediction than not only the Newtonian, but any of the other subsequent theories that we can look at there. Again, if we then jump to the Carrignan 2013 sample, again, the same reasons as to why we chose this one, okay? Here are the input parameters again, huge variation in luminosity, huge variation in scale length, huge variation in distances, same plots here. Okay, once again, in here we see even a much tighter correlation that the blue line, the conformal gravity fit, seems to fit all of these very, very well. One exception here being NGC 3109, where I just hadn't had a chance to update that to the latest data fit for that one, as new data has come out on NGC 3109. Again, these are with conformal gravity being the theory that sets the mass scale for these, okay? We can do it again, letting MOND fit the mass scale. And now on this case, we're gonna see that the red line is gonna be a much better fit, whereas conformal gravity is now missing. But the takeaway here is that no matter which theory we use, if we look at the columns which have the mass to light ratios of mass to light ratio sub C and mass to light ratio sub M, no matter which one we use, these are acceptable mass to light ratios that still fall roughly on the order of unity. Okay, let's jump to the Tully Fisher relationship. First, we'll introduce it, and then we'll talk about how it goes into these particular surveys, okay? What is the Tully Fisher relationship? It seems to be an empirical observation, right? So this is kind of similar to Kepler's laws, right? There's no mathematical proof currently until we explain something coming up in a little bit for this relationship, but what it basically says is that for a given galaxy, if you take the last data point that you can possibly observe about that galaxy, you take its velocity and you raise it to the 4th power, that number usually comes out pretty much proportional to the mass of that galaxy. It seems to be some sort of universal thing that galaxies are obeying, which is important for us, right? Because we said that something like, if we're going to put dark matter into a system, there currently seems to be no universal solution. So anything that points to universality is going to be key for understanding what is actually going on in these systems. But more importantly, if you are going to propose an alternative theory like conformal gravity or MOND, then it has to be something which looks more universal than the dark matter theory, okay? This is just me repeating what I just said here, okay? So let's turn again to conformal gravity and say, well, can conformal gravity actually give us a prediction for the Tully Fisher relationship? And if it actually turns out that we can, if we go back to this rotation curve velocity formalism that we had a couple minutes ago and a couple of other slides, and we take the asymptotic limit, and we're going to neglect that quadratic term. I'm only neglecting the quadratic term because, again, that only shows the turnover in the largest of galaxies, none of which are in any of these samples here, okay? So we can neglect that K term, and then we square that whole thing. So now we have a formula that, well, if we have V squared, then we can get V to the 4th by just squaring it. And if we do that math and we take it in the limit such that we're past the point where the Newtonian fall off is just totally missing, we can get a nice concise formula, which is down here, such that V to the 4th is this parameter B, which is just given by a bunch of constants of nature, multiplied by the mass, right? So if we ignore that 1 plus n star over d term, then right now we see an exact Tully Fisher relationship. V to the 4th is equal to something times the mass. But conformal gravity goes a step further because it has this 1 plus n star over d term. And if we look at what d is, it's about 5.65 times 10 to the 10, which, by the way, 10 to the 10 is about what most galaxies, is basically what the mass of most galaxies or average spiral galaxies are. Namely, we see now not only the leading term as being V to the 4th is proportional to mass, but we have a deviation term that only the largest of galaxies will show, okay? This is very, very important for our discussion because since most galaxies are slightly smaller than that 5.65 times 10 to the 10, especially the dwarf galaxies, right? We can then basically get a range as to what is an acceptable value for the Tully Fisher relationship. And we can also test it against this departure that conformal gravity predicts, okay? So if we do this for the 2 samples, okay? If we take all the galaxies from the Bottema sample and all the galaxies from the Carrignan sample, and we pop them onto one plot, and just to keep the natural errors, instead of doing V to the 4th is proportional to M, we're going to do V proportional to M to the 1/4, so we can keep the actual error bars in the velocity there. Then what we see is that the green line is the exact V to the 4th being proportional, or I should say V being proportional to M to the 1/4. And as we see and again, on the panel on the left is with conformal gravity setting the mass scale. The panel on the right is with MOND setting the mass scale. In both of them, a majority of the galaxies sit right along this green line, namely the Tully Fisher line, which is great. But the largest of the galaxies are off the line. But not only are they off the line, they're going right according to this orange line. And that orange line is the line that shows this formula here that comes from conformal gravity for v to the fourth. Namely, it shows the departure. And what it's showing us is that no matter which theory, whether it's conformal gravity or MOND, no matter which one sets the mass scale, both of these are showing the conformal gravity departure. This is extremely important because, like we said, Tully Fisher was supposed to be just an empirical formula that comes from the data. This is not supposed to come from first principles. It doesn't come from first principles in standard gravity. But here, in conformal gravity, we not only get a v to the fourth being proportional to m, we get an orange line deviation. And it looks like, at least for these galaxies in this sample, it looks like those galaxies are hugging this line, which is very important if we're going to provide some sort of test between an alternative theory and the standard theory. But again, the key takeaway here is that for both conformal gravity or MOND setting the mass scale, they both happen to hit that deviation line. This is a pretty awesome, pretty new result that that no one has seen before, and so we're happy to present it here for the first time, at least for this sample. Okay. Here I'm talking about the importance of the deviation, but I just talked you through it. Now, again, back to this issue that we said a minute ago, okay? Another piece that we haven't finished the research on, but this is one of the places where we'll be moving into work in the future, is that Tully Fisher is important because it is this empirical data that seems to always happen for galaxies. But here's the caveat, is that it happens so often in galaxies that now astronomers will use or will assume that Tully Fisher has to be present in every galaxy, that will use Tully Fisher in order to get estimates for the distance. But remember, to test against Tully Fisher, it means that you need to know the mass. But to get the mass, you first need to know the distance. And so now we've come around to this circular argument that if we assume Tully Fisher gives us the distance, we should therefore not be able to use Tully Fisher to get the mass. If we get the mass from some other mechanism and then use Tully Fisher to get the distance, that's okay. But we can't go in the circle where we use Tully Fisher to get the distance, and then we use the distance, which already came from Tully Fisher, to get the mass, because then we'd be presupposing that Tully Fisher exists, and then of course we'd be right along the green line, even if nature didn't want us to be there, namely, what if nature wanted there to be a departure? I bring this up because if we go to the NASA extragalactic database and look up what is the distance to a particular galaxy, here is one taken straight from the website for NGC 2841. And if we look, I can't even count this, this is about 25 or 30 distance measurements. And if we look at the distances, it ranges from 13.1 megaparsecs all the way up to 21.6 megaparsecs. This is a huge, huge deviation. It's almost a factor of 2. But next to it, it has the method as to how these distances were calculated. We know in the science now in astronomy that Cepheids operate as great standard candles. So if you have Cepheids, you should use those for the distances, which is how we did all the distances for these surveys. We only used ones that were from Cepheid measurements and took the average. However, if you look down, right at around the one that starts here, my pointer at 11.2, and then going up to 21.6, all of those distance methods were assuming Tully Fisher to be true, and look at the variation when you assume Tully Fisher to be true. So we see this as a way in the future of potentially, now that we know a deviation might exist, we use the deviation, or we assume conformal gravity to get the mass scale and see if we can get a predictable distance from that. That will be a future work. Let's go to the RAR analysis for these two sets of galaxies. So we take each one of those data points in the rotation curves and we plot the v squared over r for the observation versus the prediction. Okay, The blue panel, again, this is using conformal gravity to set the mass scale. The top left panel shows that scatter plot of those centripetal accelerations, which does have this nice shape, which Mogolley and Schoenberg predicted, okay? But if we use conformal gravity as an alternative method and say there should be no dark matter, then what we see is that the conformal gravity theory, when overlaid in purple, predicts the coverage of this plot. But moreover, if we replace the x-axis as the prediction from the luminous matter alone, using conformal gravity as the prediction, as opposed to using Einstein as the prediction, we see something very amazing. And that is that those lines all coalesce in this orange plot in the top right. They all coalesce around the line of unity, showing that if we use that as the proper theory, then yes, there would be no dark matter in the system. There would only be the luminous matter. If we do the same using MOND as the thing that sets the mass scale, we get very, very similar conclusions. I do point out one particular thing here. We have this line in green here in MOND that I did not bother putting on the conformal gravity slide a minute ago. The reason being is that, remember, in the Mogolley and Schoenberg analysis, they had this nice line that went through the data points. This is that same line, and we see that if we use only these data points from these two surveys, we see that that line doesn't exactly capture all the data points as well as it did for their sample, meaning that there might be some variation in this line depending on the sample that you use. So that's our conclusions for the radial acceleration rule. The overall conclusions of this talk, and I want to make sure that there's plenty of time for questions, is that when we use the latest distance measurements from Cepheus, both MOND and conformal gravity can account for these two surveys quite well in the rotation curves, Tully Fisher, and the radial acceleration rule. This is great news for alternative gravity. Tully Fisher, though, should not only be used as a test. It should not be a given. And conformal gravity now, as an alternative theory of gravity, allows for deviations to be shown in the data and gives a first principles derivation as to how these deviations should be calculated. And we've seen that those deviations can be shown in these two samples. And this is a very small sample size, but in these two samples, we can already see it there, and we can see it not even unique to conformal gravity as setting the mass scale, but also to MOND setting the mass scale. So there does seem to be way more universality there than anyone might give at first consideration. Lastly, the initial Radial Acceleration Rule formalism does not completely align with CG or MOND, but both can give a fundamental prediction for the Radial Acceleration Rule without the need for dark matter. I already talked about future work. One will be this kind of trying to remove this circular argument for Tully Fisher, and excuse me, code writing for that is already underway, and that will be one of the things that I'm pursuing this summer. And obviously, you know, this was just for two particular samples. Now that we have the ability to take the MOND, the conformal gravity, dark matter, general relativity, and the MLS formalism and get them on one singular rotation curve plot and do the Tully Fisher, do the radial acceleration rule, galaxy by galaxy, survey by survey comparison will be great. And there has already been some authors at this conference that already had some data, some galaxies that we currently don't have. And so I'm looking forward to partnering with people like Paolo Salucci and Asher and some other people that were at this conference today, and Howie. There's a lot of work that can be done. I think that one of the things that we showed is that a lot of us are working on the same types of problems. We're attacking the same problems from different lenses and coming to slightly different solutions. And one of the great things about these conferences is that it brings us together. It allows us to share these ideas, and it allows for this collaboration to happen. And so I'm looking forward to the next coming weeks after we digest this and we all get some rest from waking up at 4 in the morning for this conference. But I'm looking forward to the next couple of weeks and exchanging that data, exchanging the ideas, and seeing what the next year looks like. And then 2 years from now, when we meet for IARD again, I think that we're all going to have a lot to say. So thank you for your time. I'm going to throw it over to the other room now for discussion. So thank you again to IARD. Thank you to Peter for trying to set this up in Prague. Obviously, we're not in Prague, but hopefully we'll be there soon enough. Thank you to all my colleagues. Thank you to the organizers, and thank you to Springfield College for allowing me to continue working on this great research. So I'm happy to take any questions, comments, complaints, and concerns.